Assalamu alaikum students. I am Dr. Muhammad Munir Omar. I welcome you all to the course CS371 Data Communication and Networks. Today we will be studying multiple access protocols in this lecture. The main contents of our today's lecture are multiple access. We will know the basic concept about the multiple access, having some examples. Then we have some protocols to be studied. We have CSMA, Carrier Sense Multiple Access, CSMA-CD, Carrier Sense Multiple Access Collision Detection, then CSMA-CA, Carrier Sense Multiple Access Collision Avoidance. After that, we have reservation, polling, and token passing. These three protocols are known as random access protocols, and these three protocols are known as control access protocols. So in this lecture, we will be studying all these six protocols. In the previous lecture, we studied about the IEEE standard, where we saw that the data link layer is divided in two parts. The first part is data link control, and the second part was MAC, media access control. The upper layer is responsible for the flow and error control, while the lower layer, that is mostly responsible for multiple access control or multiple access resolution. So our main concern in today's lecture is multiple access resolution, which is the lower part in the data link layer. When nodes or stations are connected and use a common link, this is obvious that in network many nodes use a single medium to connect each other. We can say that there would be fewer connections among multiple nodes, and those connections or those mediums would be shared among the different nodes. The communication can be multi-point or broadcast. We need a multiple access protocol to coordinate access to the link. The problem of controlling the access to the medium is similar to the rules of speaking in a gathering. Suppose we have a cocktail party where many people gather in a large room and they communicate with each other by using the air as a medium. This can also be a classroom where we have many students sitting and listening to a lecture and also do participate in the class. So there must be some sort of protocols for communication in such type of activities like party or classroom. So the first protocol is that, or the rule is that, give everyone a chance to speak. Second, don't speak until you are spoken to. Don't monopolize the conversation. Raise your hand if you have a question. Don't interrupt when someone is speaking. And don't fall asleep when someone else is talking. So these are the rules which must be obeyed by all the participants or all the people who are in a gathering and want to communicate with each other. In the same way, we have some sort of similar rules for data communication in which multiple nodes share some common medium and do communicate with each other. So we have LANs, Wi-Fi, satellite networks, and also the cocktail party. If more than two users send at the same time, simply say that if more than two persons speak at the same time, what would happen? There would be a sort of collision. Now, if there is collision, then what will happen? All the collided packets will be lost, and this would cause the waste of bandwidth. Ideally, the MAC protocol for a broadcast channel with the bit rate or bits per second should satisfy. If only one node is sending, then throughput is R. If M nodes have data to send, then the throughput is R by M. So these are the multiple access protocols. We have random access protocols, controlled access protocols, and channelization protocols. Under random access protocols, we have Aloha, CSMA, CSMA-CD, and CSMA-CA. And under controlled access protocol, we have reservation, polling, and token passing. Also, under channelization protocol, we have FDMA, TDMA, and CDMA. In today's lecture, we will be looking into CSMA, the carrier sense multiple access, collision detection and collision avoidance, and also the reservation, polling, and token passing. So what is random access? In random access or contention method, no station is superior to any other station and none is assigned to control over another. We must treat all the stations as similar. There is no inferior, no superior. Everyone must be given a chance to communicate. No station permits or does not permit another station to send. There is no sort of power, or you can say that no station has any authority to permit or not permit any other station to participate in the communication. At each instance, a station that has data to send uses a procedure defined by the protocol to make a decision on whether or not to send. If a node wants to send some data, then it must follow a procedure for sending that data. So according to that procedure, the node would either send that data at the same time or wait for a suitable time to send its data. Now we have carrier sense multiple access, CSMA. CSMA was invented to minimize the collisions and increase the performance. To minimize the chance of collision and therefore increase the performance, the CSMA method was developed. The chance of collision can be reduced if a station senses the medium before trying to use it. So the station follows the activity of other station, or simply we can say that it senses the medium, whether that medium is used by other stations or not. The CSMA requires that each station first listen to the medium or check the state of the medium before sending its own data. We have simple rules, just like human conversation. Listen before talking. If someone else begins talking at the same time, then stop talking and wait for the other person to stop and then resume your conversation. So we have CSMA. A node should not send if other node is already sending. This is carrier sensing. And then we have collision detection. A node should stop transmission if there is interference. Next, we have persistence methods. We have two questions. First, what should a station do if the channel is busy? Or what should a station do if the channel is idle? So, to handle these two questions or to act according to these two, we have three methods. These three methods are known as persistence methods. First one is I persistent, then non-persistent, and the third one is P persistent. So first, the I persistent. It's simple and straightforward. After the station finds the line idle, it sends its frame immediately with a probability I. This means that the highest chance of collision, because two or more stations may find the line idle at the same time and may send their frames immediately. Suppose we have a medium, station A and station B are connected with this medium. Both find this station as this medium as idle, means that nobody is using this station at the same time T, and both send their frames at the same time. So what will happen? These frames will be transmitted at the same time, and these both frames will collide with each other. So the chances of collision in I persistent are very high. Its flow diagram is also quite simple. The station look into the medium or the channel, and if the channel is busy, then it resends it or sends it again, and if the channel is idle, then the station transmits its data. Here the station continuously senses the channel. If the channel is busy, then it senses it it senses the channel again, and if the channel is idle, then it transmits the data. This was about I persistent. Next is non-persistent. A station that has a frame to send senses the line, same as the previous case. If the line is idle, it sends immediately. If the line is not idle, it waits a random amount of time and then senses the line again. So here, if you look into this figure, there is a bit difference. Here, the station is continuously sensing the channel, while in case of non-persistent, the station senses the channel. If it is busy, then it waits for a random period of time. It's random. If we look into this figure, this wait time is a bit smaller than this one, so we can see that the wait time is random, not fixed. If the line is not idle, it waits a random amount of time and then senses the line again. The non-persistent approach reduces the chance of collision because it is unlikely that two or more stations will wait at the same amount of time and retry to send simultaneously. So here the chances of collision are a bit lower as compared to this one, because we are using a random wait time, so each station will have different wait time and there would be a bit less chances of collision for these random wait times. However, this method reduces the efficiency of the network because the medium remains idle when there may be stations with frames to send. Now, if we put this wait time, then it is possible that the station may lose an idle time, or the channel may be kept idle for a longer time. So in non-persistent, the efficiency is quite low, but the chances of collision are also less. If you look into the flow diagram, here we have one additional component. If the channel is busy, then the station must wait for a random period of time and then sends the channel again. And if the channel is idle, then it must transmit its data. Next is p persistent. This is a probability based method. It is used if the channel has time slots with a slot duration equal to or greater than the maximum propagation time. So if the station finds the line idle, it follows the following steps. First, with probability P, the station sends its frame. With probability q equal to 1 minus p, the station waits for the beginning of the next time slot and checks the line again. Then, if the line is idle, it goes to step 1. If the line is busy, it acts as though a collision has occurred and uses the backup procedure. Now, here the station is continuously sensing, and if it finds the channel as idle, then check the probability outcome and check whether to transmit or not. There we will have some time slots according to the outcome, and according to the steps the data would be transmitted, or the step number 1, which was about the probability, will be calculated again. So here step number 1 was probability P. Now the channel is checked whether it is busy or idle. If it is busy, then the station will sense the channel again and again. There is no wait time here. After that, if the channel is idle, then the probability outcome would be checked. So if it is less than or equal to P, then the station can transmit its data. And if it is greater than P, then it would wait for next slot and check the channel again. If it is idle, it would go back to step number 1, which is about the probability P. And if it finds that the channel is busy, then it would use the backup process as though collision occurred. In case of CSMA, the carrier sends multiple axes. There was no proper specification for the collision. We can say that there was no detection mechanism whether the transmitted packets are collided or not. So we have CSMA CD, carrier sends multiple axes with collision detection. CSMA CD arguments the algorithm to handle the collision. In this method, a station monitors the medium after it sends a frame to see if the transmission was successful. If the transmission was successful, then it is considered as finished, and if it was not successful, then there would be a collision and the frame is sent again. To better understand the CSMA CD, let's have a look at the first bit transmitted by two stations involved in the collision. Although each station continues to send bits in the frame until it detects the collision. So we show what happens at the first bit collide. In this figure, we have station A and C, both are involved in collision. Both are sending one bit at the same time. At time t1, station A has executed its persistence procedure and starts sending the bit of its frame. At time t2, the station C has not yet sensed the first bit by A. Station C executes its persistence procedure and starts sending the bit in its frame, which propagates both to the left and to the right. The collision occurs sometimes after time t2. Station C detects a collision at time when it receives the first bit of A. Station C immediately, or after a period of short time, aborts transmission. Station A detects collision at time t4 when it receives the first bit of C. It also immediately aborts transmission. So if we look into the figure, A transmits for the duration of T4 from T1 to T4, while C transmits from T2 and T3. At the time T4, the transmission of A's frame, though incomplete, is aborted, and at time T3, the transmission of C's frame is also incomplete and aborted. So look at the figure again. The station A started its transmission, or transmitted its first bit from time t1 to t4. So this is the transmission from A. This A's bit is on the channel for the propagation delay. It is tilted downward. At time t2 and time t3, the station C transmitted a bit of its frame. Now this one is for C. Now if you look into these both parts are colliding here somewhere between the T2 and T3. Now the station C would detect this collision at time T3, and also the station A would detect this collision at T4. Actually at T4, the station A would receive this bit from C, and also the station C would receive the A's bit at time T3. So at T3, the C would detect the collision and abort its transmission, and also at T4, A will detect the collision and abort. The basic idea behind CSMA CD, the collision detection, is that a station needs to be able to receive while transmitting to detect a collision. While there is no collision, the station receives one signal, its own signal. When there is a collision, the station receives two signals, its own signal and the signal transmitted by a second station, its own signal and also a signal transmitted by another station. To distinguish between these two cases, the received signal in these two cases must be significantly different. In other words, the signal from second station needs to add a significant amount of energy to one created by the first station. While note one thing, that in wired networks, the received signal has almost the same energy as the sent signal, because either the length of the cable is short or there are repeaters that amplify the energy. In simple words, we can say that there would be very less energy loss in wired networks. So this would mean that in case of a collision, the detected energy would be almost double due to the reception of uh, signals from two sides, on signal and from the other station. However, in wireless networks, much of the sent energy is lost in transmission. The received signal has very little energy, therefore, a collision may add only 5 to 10% additional energy, means that the detection would be a bit difficult due to the energy loss of the received signal. So, this is not useful for effective collision detection. We need to avoid collisions on wireless networks because they cannot be detected due to the lost energy. The carrier sense multiple access with collision avoidance CSMA CA was invented for this type of network for wireless networks. Collisions are avoided through the use of CSMA CA by using three strategies: the interframe space, the contention window, and acknowledgements. So we are looking into these three strategies now. These are used for collision avoidance and particularly target the wireless networks. So the first one is IFS, interframe space. First, collisions are avoided by deferring transmission even if a channel is found idle. When an idle channel is found, the station does not send immediately. In other cases, we saw that if the channel is found idle, then a device or a station could send its data immediately, but here it cannot send the data immediately. It waits for a period of time, and this time frame is called IFS or interframe space. Even though the channel may appear idle when it is sensed, a distant station may have already started transmission. We have seen this thing in previous figure that two nodes started transmission at almost the same time. Actually, both sensed the medium at the same time and they immediately started their transmission. The distant station's signal has not yet reached the station. The IFS time allows the front of the transmitted signal by the distinct station to reach this station. If after the IFS time the channel is still idle, the station can send. So it must wait for IFS. After that, it is allowed to send its data, but it still needs to wait a time equal to the contention time. The IFS variable can also be used to prioritize stations or frame types. For example, a station that is assigned a shorter IFS has a higher priority. Next is contention window. The contention window is an amount of time divided into slots. A station that is ready to send chooses a random number of slots as its wait time. The number of slots in the window changes according to the binary exponential backoff strategy. This means that it is set to one slot the first time and then doubles each time the station cannot detect an idle channel after the IFS time. This is very similar to p persistent method, except that a random outcome defines the number of slots taken by the waiting station. One interesting point about the contention window is that the station needs to sense the channel after each time slot. However, if the station finds the channel busy, it does not restart the process. It just stops the timer and restarts it when the channel is sensed as idle. This gives priority to the station with the longest waiting time. The last strategy is acknowledgement. With all the precautions, still there are chances of collision resulting in destroying data. Even if we apply the other two strategies, we may get collision. So the last thing is acknowledgement. In addition, the data may be corrupted during the transmission. The positive acknowledgement and the timeout timer can help guarantee that the receiver has received the frame. So if we apply these three strategies, then the collision can be avoided in the networks and particularly in the wireless networks. Next is controlled access protocols. So we are going to study the reservation, polling, and token passing now. The controlled access. In the controlled access, the stations consult one another to find which station has the right to send. A station cannot send unless it has been authorized by other stations. We will discuss three popular controlled access methods in the coming slides. The first one is reservation access method. In the reservation method, a station needs to make a reservation before sending data. Time is divided into intervals. In each interval, a reservation frame precedes the data frame sent in that interval. In this figure, we have 5 stations. So for each station, there is one mini slot. So we have 5 mini slots. These all are reservation frames. In the first interval, station number 1, 3, and 4 made reservations and transmitted their data, while in second interval only station 1 has made a reservation to transmit its data. The next access method is pooling. Pooling works with the topologies in which one device is designated as primary station or admin station, or we can say a powerful station. All data exchanges must be made through the primary device even when the ultimate destination is secondary device. If A want to transmit some data to B, even though the primary device must be involved in this transmission. The primary device controls the link. The secondary devices follows the instructions of primary device. The primary device determines which device is allowed to use the channel for a given period of time. Therefore, the primary device is always the initiator for a session. So if the primary device wants to receive data, it asks the secondaries if they have anything to send. This is called pool function. If the primary wants to send data, it tells the secondary to get ready to receive the data from primary. And this is called select function. Here we have select function and here we have pool function. Select is used for getting data from primary device, while pool is used to ask the secondary devices whether they want to send any sort of data. So first check the select function. The select function is used whenever the primary device has something to send. As we know that this primary device has control over the link. So whenever it wants to send some data, it must ask the secondary device. If it has something to send, the primary device sends it directly. What it does not know, however, is whether the target device is prepared or not. Sending is not an issue for primary device, but the issue might be that whether A and B these are prepared for receiving or not. So before sending, the primary creates and transmits a select frame, SEL frame, which is acknowledged by the secondary device if it is prepared or ready for reception. So once the primary device gets the acknowledgement ACK, after that it starts data transmission towards that target secondary device. In the next function, the pull function, primary device receives data from the stations. It must ask each station in turn if it has anything to send. When the first secondary is approached, it responds here with negative acknowledgement, means that A is not sending any data to primary, that it hasn't any data prepared for transmission. So after that, the primary device again sends a poll to system B or station B, and B has something to send, so it directly sends that data to primary device. Upon reception of this data, the primary device acknowledges the successful reception of data. So this was about the pooling access method. The last method is token passing access method. We have already studied about the token ring topology. In the token passing method, the stations in a network are organized in a logical ring. Each station is connected with two devices on both sides. So the connections create or shape a ring. So in the ring, there are two things, the predecessor and successor. The predecessor is the station which is logically before the station in the ring. So for 2, the predecessor is 1, while the successor for 2 is 3, which is after 2. And the current station is the one that is accessing the channel now. The right to this access has been passed by the predecessor to the current station. The right will be passed to the successor by the current station. For this purpose, a special packet is circulated among all these stations. So each node having that packet takes the control over the medium. If that packet is received by 2, then this 2 would be the current station. It has right to transmit data. Its predecessor would be 1, means that packet, that control packet is received from 1, and ultimately after completing its transmission or transmitting data, this 2 would transfer that control packet to its successor number 3. We can have a dual ring topology in which we use one auxiliary ring in the reverse direction. The second ring is for emergencies only. If one of the link in the main ring fails, then this auxiliary ring will be used. This is used by FDDI, Fiber Distributed Data Interface, which is high-speed token ring network. The devices are connected through fiber optics, and two fiber optics are designed to connect these devices, or we can say that there would be two rings made of fiber optics. One is the second primary ring, and the second one is the secondary ring. Third case is the bus ring topology. Here, the devices or the stations are connected to a single bus. Each station knows the address of its successor and also predecessor. Here in the ring, the successor and predecessors are already known, but in this case, they must know in advance about their successor and predecessor. Only the station with the address matching the destination address of the token gets the token to access shared media. The last case is star ring. This is actually the physical topology, the ring topology, and uses a hub, a central device. However, the hub here is only a connector. Wiring inside this hub makes a ring. These stations are connected to this ring through two wire connections. This topology makes the network less prone to failure because if a link goes down, it will be bypassed by the hub and the rest of the stations can operate. Also, addition and deletion of nodes is easy in this star ring. So in today's lecture, protocols we studied were CSMA, carrier sense multiple access. This was about the sensing of media, and then CSMA CD, carrier sense multiple access collision detection. With sensing, the detection is also performed in the second protocol. And the third one was CSMA CA. CA means CA stands for collision avoidance. In case the detection is not possible, this can be not possible in wireless networks particularly. So for that purpose, the CSMA CA can be used. We also studied about the reservation, pooling, and token passing. These slides are prepared from Data Communication and Networking, 5th edition by Behrouz Ferozan. If you have any question, you can put your comments in the KCMS. Thank you. Allah Hafiz.